We are taught, from the first physics class we ever take, that time is one thing and space is another. Time ticks, space extends. They feel like different categories of phenomenon, the way sound feels different from color. But at the deepest level of physics, the difference between time and space is exactly one thing. It is a minus sign in front of one term in an equation. That is all. A single minus sign carries the entire flow of cause and effect, the entire experience of past and future, the entire reason memory works and prediction does not. And the minus sign, in most of the universe, sits firmly in front of the time term. In one specific environment, in one specific kind of object that we have already photographed twice, that minus sign moves. It slides from one coordinate to another. The radial direction becomes the time direction. The time direction becomes a direction in space. Get comfortable. Hit subscribe if you're new here, because by the end of this, the words space and time will never sit in the same relationship to each other again. Now, let's slowly ease into this. Part 1. The two words we never question. There are two words you use almost every day without thinking about them. Space, time. You say, "Give me a little space," and you mean a small physical distance, a few feet, a foot, the breadth of an arm. You say, "Give me a little time," and you mean a small duration, a few minutes, an hour, the breadth of a thought. The words feel obvious. They feel like the most settled vocabulary you possess. Space is the stage. Time is the music. The stage is wide, and you can walk across it. The music plays in one direction, and you cannot rewind it. That is what those two words mean, and you have never had a reason to question them. Tonight we are going to question them. We are going to question them slowly, because the question is patient, and the answer is unhurried. We are going to question them carefully, because a careless answer here is worse than no answer at all. And we are going to question them honestly, because the punchline of this video is not a metaphor and it is not a flourish. The punchline is a fact, embedded in an equation written by a 41-year-old artilleryman in a tent on the Russian front in the winter of 1915, while shells exploded a few hundred meters away. The fact is this. Inside the event horizon of a black hole, the words space and time no longer mean what they mean for you. Here, on the surface of the Earth, in this chair, on this evening. Inside the event horizon of a black hole, the coordinate you would have called distance becomes the coordinate that carries the flow of cause and effect. The coordinate you would have called time becomes a direction, a thing you can walk across or stand still on. The roles do not blur, they swap. This is not a way of speaking. It is not a poetic gloss on something more mundane. It is a sign in an equation, and the sign flips at a particular surface in space, and the flip changes everything on the other side. But before any of that lands, I want to take you all the way back to the beginning. Not to the beginning of black holes, to the beginning of what those two words, space and time, are actually built from. So let us start almost from rest. You are sitting somewhere. The light around you is steady. The temperature is comfortable. You feel that you exist at a particular place wherever your body is, and that you are moving forward through time at a rate of roughly 1 second per second. The chair is at a place. The hour is a duration. You have an intuition about each. The intuitions feel symmetrical. Space and time, you assume, are different kinds of things, but they are both background containers. You are an object. You sit in space. You unfold through time. The containers do not change. They just are. This intuition is, of all the intuitions humans have, one of the most useful. It will get you through almost any waking moment of an ordinary life. It will let you drive, walk, plan, remember, anticipate, sleep. It will let you do every single thing you have ever done. There is nothing wrong with it. It is the right intuition for the environment you evolved in. It is also, in a very precise sense, provincial. To say an intuition is provincial is not to say that it is wrong. It is to say that it works in one neighborhood and stops working when you leave. The intuition that the ground is flat is provincial in this way. On a kitchen floor, on a soccer field, on the surface of a frozen lake, the ground is flat enough. It is only when you sail far enough from shore, or when you walk far enough north, or when you draw a triangle of sufficient size, that you discover the ground was not flat. It had a curvature you could not feel. Space and time, taken as separate background containers, are a flat earth intuition. They work in the neighborhood you live in. They stop working when you walk far enough from any large mass, or fall far enough toward one. There is no warning that they have stopped working. The breakdown is silent, and the boundary is invisible. We are going to find that boundary tonight. We are going to find it by going through a sequence the universe would walk you through if it had a teacher's patience. We are going to start with the cleanest, simplest, most idealized case-flat, empty space-time, infinitely far from any mass, where the two intuitions still hold. We are going to introduce a single rule about the relationship between space and time in that empty environment, and we are going to take that rule completely seriously. Then we are going to drop one heavy thing into the picture. A single, perfectly spherical, perfectly motionless mass. We are going to write down, using the equations Einstein wrote down in the autumn of 1915, the geometry that surrounds that mass. And we are going to read what it says. What it says, when you read it carefully, is that there is a surface around that mass, an invisible spherical surface, no thicker than nothing, where the difference between space and time, the very thing that lets the words have separate meanings, is about to flip. Outside the surface, you live in the world you know. The chair you are sitting in is at a place. The minutes are passing in a direction. You can move in any direction in space. You cannot move in any direction in time. Inside the surface, all of that has rotated by 90 degrees. I am not going to ask you to believe this yet. I am going to ask you to follow the math slowly with me. The math is not difficult. There is exactly one number to track, exactly one sign to watch, and exactly one rule about that sign. Everything else flows from those three things. And by the time we finish, you will not need me to convince you of anything. You will see it for yourself, the way physicists eventually saw it for themselves, except it took them 44 years to see what was inside an equation they already had. For now, just notice the chair you are sitting in. Notice the way the chair is at a place. Notice the way the minutes are passing. Notice the calm, mundane separation between the two. That separation is the thing we are going to dismantle, slowly, very gently, for the next 2 hours. The dismantlement is not violent. The chair is fine. The room is fine. You are fine. What is changing, tonight, is the rule that makes the chair a place rather than a moment. And that rule, it turns out, is not universal. It is local. It holds where you happen to be sitting because of where you happen to be sitting. There are places in this same universe, observable with telescopes, where the rule no longer holds. We have photographs of objects with such places inside them. We have heard, in gravitational-wave data, the last few milliseconds of mergers that produced exactly such regions. So let us begin. Let us begin with one quantity that is going to be the single most important quantity in the whole video. It is called the space-time interval. It is the way the universe measures distance. It is also the way the universe measures duration. And the secret of black holes, the secret we are working toward, is that the space-time interval cannot tell the difference between those two things except by a sign. Part 2. What a space-time interval is. Imagine you and I are sitting in different rooms in the same building. There is a clock on each of our walls. there is a tape measure stretched between us. If a firecracker goes off in my room at noon, and a firecracker goes off in your room at 1 minute past noon, how would we describe the relationship between those two events? We would describe it with two numbers. We would say the events were separated by some distance the length of the tape measure between our two rooms, which is fixed. And we would say they were separated by some time, the 1 minute that elapsed on both of our wall clocks, which is also fixed. That feels like a complete description. Distance and time. Two numbers, two intuitive notions, nothing left over. It is a complete description. In the same way that telling you it is 12 degrees and the wind is blowing northeast is a complete description of the weather. It is complete enough for almost every purpose, in almost every neighborhood, but it is missing the deeper thing, the thing that makes both numbers work together. The deeper thing is what physicists call the space-time interval. The space-time interval is, in plain English, the size of the gap between two events measured by the universe itself in a way that everybody agrees on. That second part is the important part. Everybody agrees on. Because in special relativity, which Einstein wrote down in 1905, different observers do not agree on distance. They do not agree on duration either. If you are at rest in one room, and I am moving past you on a fast train, your tape measure and my tape measure will read different things for the same pair of events. Your clock and my clock will read different things too. The numbers are not absolute. They depend on who is measuring. Einstein's discovery, the one that broke everything that had come before it, was that there is exactly one combination of distance and duration that does not depend on who is measuring. Every observer, no matter how they are moving, gets the same answer. That combination is the space-time interval. It is built from two ingredients. The first ingredient is the spatial distance between the events, the length of the tape measure, the change in x. The second ingredient is the temporal distance between the events, the change on the wall clock, the change in t. The space-time interval is the spatial distance squared, minus the speed of light times the temporal distance, also squared. Or, depending on which convention you use, the speed of light times the temporal distance squared, minus the spatial distance squared. The two conventions just put the minus sign on opposite sides of the subtraction. They describe the same physics. What matters is that there is a minus sign. There is always a minus sign. Between space and time, in the very fabric of the universe's measurement of separation, there is a minus sign. Stop with me on that for a second. Distance squared plus distance squared plus distance squared for three spatial dimensions gives you the ordinary distance through space, the kind Pythagoras would have written down. All three terms are positive. They add up. That is what makes space space. Time squared subtracted from those distances, or equivalently, distance subtracted from time squared, that minus sign is what makes time time. The minus sign is the difference. That is the whole story. There is no other distinction between a spatial dimension and a temporal dimension at the deepest level of physics. There is just a sign, and the sign tells you, in the most concrete possible way, that time is a different kind of dimension from space. Now, what does this minus sign do in practice? It does a few things, and each of them matters for where we are going. First, it sorts events into three categories, depending on the sign of the resulting interval. If the interval is negative, under one common convention, the one I will mostly use tonight, the two events are time-like separated. That means there is enough time between them, compared to the distance, that a slower-than-light signal could have gotten from one to the other. The events are causally connectable. The first one could have caused the second one. If the interval is exactly zero, the two events are null separated, or light-like separated. That means a beam of light traveling at exactly the speed of light, could have gotten from one to the other. Photons and only photons. If the interval is positive, the two events are space-like separated. The distance is too big for the time. Nothing, not even light, could have gotten from one to the other. They are causally disconnected. The first one could not have caused the second one. They are too far apart in space for the elapsed time to bridge them. So the sign of the interval is the universe's sorting machine for cause and effect. Negative, the events can be causally related. 0, only light could have connected them. Positive, they cannot have influenced each other. Notice what this means. The minus sign in front of time, the sign that distinguishes time from space, is what carries the entire concept of causality. Without that minus sign, every dimension would be a spatial dimension. Without that minus sign, there would be no past and no future. There would be no flow. Time is, in the most literal possible sense, a sign in an equation. Let me say that again, because we are going to come back to it. Time is a sign in an equation. The flow you feel, the sense that there is a forward and not a backward, that the past has already happened and the future has not, that you can remember yesterday but not tomorrow, all of that, the entire experience of being a creature embedded in time is carried at the deepest level by a minus sign in front of one term in the space-time interval. This is a remarkable thing to absorb, and most physicists do not absorb it on first contact. They learn the equation, they pass the exam, and they move on. But the sentence is true. The asymmetry between space and time, the thing that makes time feel different from space, is the sign of one term. Now, in flat, empty spacetime, infinitely far from any mass, that sign is fixed. The minus sign sits in front of the time term, and the time term carries the time, and the space term carries the space, and the labeling never changes. You can fly past me on a fast train, and the values of distance and duration will shift, but the sign on each will not. Time will be time, space will be space. This is the version of physics most people have heard of. It is special relativity. It is the version Einstein wrote down in 1905. It has the minus sign, but the minus sign is permanently attached to the t-coordinate. There is no drama in the labeling. The labeling is fixed. The drama starts when you add gravity. When you add gravity, the geometry of space-time stops being flat. It curves. The curvature affects the space-time interval. The minus sign is still there, but it can now be hidden inside more complicated coefficients that depend on where you are. Far from any mass, the coefficients reduce to the same simple flat formula, and you cannot tell the difference. But near a mass, and especially near a very compact mass, the coefficients change. This is where, slowly, the sign can move. This is where, slowly, the rule about which coordinate is time and which coordinate is space can rotate. This is, eventually, where the inside of a black hole lives. Not in a different equation. In the same equation, with one coefficient flipped in sign. Before we go there, before we add the mass and watch what it does, I want to introduce you to the man who first wrote down the answer. Because the equation we are about to use was not derived by Einstein, it was derived by a man named Karl Schwarzschild, and the conditions under which he derived it are part of what makes the story land. Part 3. Karl Schwarzschild on the Russian front. Karl Schwarzschild was born in Frankfurt am Main in October 1873. By his early 40s, he was one of the most accomplished astronomers in Germany. He had been the director of the Astrophysical Observatory in Potsdam since 1909, which at the time was the most prestigious astronomical position in the country. He was a member of the Prussian Academy of Sciences. He had published influential work on stellar atmospheres, on photometry, on geometrical optics, on the structure of star clusters. He had a wife, 3 children, and a comfortable house in Potsdam. He could have spent the war years in his office. He did not. When the First World War began in August 1914, Schwarzschild was 40 years old. He was Jewish. He had no military obligation. He volunteered anyway. He was given the rank of lieutenant in the artillery. He served first in Belgium, running a weather station for the army. Then he was transferred to France, calculating the trajectories of artillery shells. Then he was sent east, to the Russian front, where his job was the same to compute, with paper and pencil and a slide rule, the precise angles at which large guns should be aimed to land their shells on distant Russian positions. This is the man we are talking about. A working astronomer, in his early 40s, by the standards of his time already old, sitting in a tent in the Russian winter, calculating ballistic tables. In late November of 1915, Albert Einstein, in Berlin, delivered the final form of the field equations of general relativity to the Prussian Academy. The lectures were spread over 4 weeks. The fourth lecture, on November 25, 1915, contained the version we now use. It is one of the most important sentences ever written about the physical world. It says, in essence, the way matter and energy are distributed determines the curvature of spacetime, and the curvature of spacetime determines how matter and energy move. Geometry tells matter how to move, and matter tells geometry how to curve. The two are the same conversation. Einstein himself, when he wrote it down, did not have an exact solution to it. He had approximate solutions. He had a calculation of the precession of Mercury's orbit that matched the observed value to within experimental error. But the full geometry around even a single point mass, the simplest possible case, he did not have. Schwarzschild, on the Russian front, did it in less than 4 weeks. He had been receiving Einstein's papers as they were being published. He read the November 25th field equations as soon as the proceedings of the Prussian Academy made it to the front lines. He sat down in his tent between artillery calculations and worked out the geometry of spacetime around a single, motionless, perfectly spherical mass. He finished by mid-December. On December 22nd, 1915, he wrote a letter to Einstein in Berlin. The letter is one of the great documents of 20th century physics. It contains the equation that we will use for the rest of the night. It also contains a line, written by a man huddled in a tent, with shells exploding in the distance, that I find unforgettable. He wrote, "As you see, the war is kindly disposed toward me, allowing me, despite fierce gunfire at a decidedly terrestrial distance, to take this walk into this your land of ideas. A walk into your land of ideas. A walk from the Russian front into the geometry of the universe." Einstein received the letter and replied on January 9th, 1916. He wrote, "I had not expected that one could formulate the exact solution of the problem in such a simple way." Einstein took the manuscript to the Prussian Academy on Schwarzschild's behalf, and on January 13th, 1916, Schwarzschild's solution was presented to the assembled mathematicians and physicists of Berlin. It appeared in print in the Academy's proceedings as a paper titled "On the Gravitational Field of a Mass Point According to Einstein's Theory." Schwarzschild never saw the paper become famous. He never knew what was inside it. While he was on the Russian front, he contracted a rare and at the time untreatable autoimmune skin disease called pemphigus vulgaris. By March 1916, his condition was severe enough that he was discharged and sent home. He went to the University Hospital in Potsdam. He died there on May 11, 1916, less than 5 months after sending his solution to Einstein. He was 42. I tell you this not as historical garnish. I tell you this because the equation we are about to read, the equation that contains the secret of black holes, the equation that contains the sign flip we are going to track for the rest of the night, was written by a dying man in a war zone. He did not know what he had written. He could not have known. The objects his equation describes were not discovered for another half-century. The phrase black hole was not coined until 1967, 51 years after his death. The full understanding of what happens inside the surface, his equation singles out as special. The understanding we are working toward tonight took the global physics community 44 years to develop, working in peacetime, with universities and computers and conferences. Schwarzschild had 4 weeks in a tent. The fact that his equation contained the role swap was, in some sense, hidden from him by the very mathematics he was working in. He used the most natural coordinate system for the problem, a spherical coordinate system with a time variable he called t and a radial distance variable he called r, the same coordinates anybody would have used. Those coordinates work beautifully outside a particular surface. At that surface they break down, they produce divisions by zero, infinities, apparent nonsense. He saw the divisions by zero. He noted them. He did not interpret them. He could not interpret them. The interpretation would have required him to do something nobody in 1916 knew how to do: change coordinate systems mid-geometry, and recognize that the divisions by zero were artifacts of the labels, not features of the place. His equation contained an event horizon. He did not know it was an event horizon. His equation contained an interior in which the radial coordinate is the time coordinate. He did not know that either. The math was correct. The math was complete. The math was on his paper. The math just had to wait for somebody to look at it the right way. The somebody, in the end, was not one person. It was Arthur Eddington, in 1924, who wrote down a coordinate transformation that smoothed out the apparent pathology and then did not realize what he had done. It was David Finkelstein, in 1958, who finally said the thing out loud. The surface at the divisions by zero is not a singularity. It is a one-way membrane. You can fall through and you cannot climb back. It was Martin Kruskal in Princeton and George Sekeres in Australia, both in 1960, who independently produced the coordinate system in which the entire geometry, both sides of the horizon, could be drawn on a single page. And it was Roger Penrose in the late 1960s who introduced the conformal diagrams in which the singularity is drawn horizontally, because the singularity is, in fact, a space-like hypersurface in the future. 44 years between Schwarzschild's letter and Kruskal's Sekeres, 44 years before the equation could be read. The space between Schwarzschild's tent and a Penrose diagram is the space we are going to walk across in this video. The walk is short on the page and long in the history. We will take the walk slowly. We will keep coming back to the man in the tent, because his equation is the equation we are reading, and the silence around him as he wrote it is, in a small way, the silence we are listening to right now. So let us read it. Let us read the Schwarzschild line element, the single equation that contains the entire story of the inside of a black hole. Part 4. The metric on both sides of the horizon. The Schwarzschild line element is a description of how to measure the space-time interval between two nearby events in the curved geometry that surrounds a single spherical mass. I am going to read it to you, in words, slowly. Then we are going to look at the one part of it that matters for tonight. Everything else is decoration. The space-time interval squared, in Schwarzschild's coordinates, is the sum of 4 terms. The first term is minus the quantity 1 minus r sub s over r, multiplied by c squared, multiplied by the change in t, squared. The minus sign in front, that is the minus sign we just talked about, the minus sign that separates time from space. The r sub s in the bracket is a particular number we are going to define in a moment. The r in the denominator is your current distance from the center of the mass. The c is the speed of light. The change in t is the change in the time coordinate. The second term is the reciprocal of the same bracket, 1 over the quantity 1 minus r sub s over r multiplied by the change in r squared. Notice that the bracket appears here too. It appears in the time term as a multiplier, and it appears in the radial term as a divider. The same bracket on both sides with reciprocal roles. The third term is r squared, multiplied by the change in the angle theta squared. This is the angular contribution from moving in latitude on the sphere of radius r. The fourth term is r squared, multiplied by sine squared theta, multiplied by the change in the angle phi squared. This is the angular contribution from moving in longitude on the sphere of radius r. The angular terms, the third and fourth, are familiar. They are exactly what you would get for a sphere of radius r in flat space. The sphere of radius r is a perfectly ordinary two-dimensional surface, embedded in our three-dimensional space, with the area you would expect, 4 pi r squared. The angular terms do not do anything dramatic. They are just bookkeeping for the fact that you are working in spherical coordinates. All the action is in the first two terms, the time term and the radial term, both of which contain the bracket 1 minus r sub s over r. Let us define r sub s. The number is called the Schwarzschild radius. It is 2gm over c squared, where g is Newton's gravitational constant, m is the mass of the central object, and c is the speed of light. Plug in numbers, and you get specific values for specific objects. For a one solar mass object like the Sun, the Schwarzschild radius is 2.953 kilometers, about the size of a small town. The actual Sun is much bigger than this, about 700,000 kilometers across, so the Schwarzschild radius is buried deep inside the actual Sun, where the equation does not apply, because the equation assumes empty space outside the central mass. The Sun is not a black hole. Its surface is far outside its Schwarzschild radius. For Earth, the Schwarzschild radius is 8.87 millimeters, about the size of a marble. To turn the Earth into a black hole, you would have to compress all of its mass, every continent, every ocean, every molecule of every living thing, every atom of every rock, every speck of dust in the atmosphere, into a sphere the size of a marble. For Sagittarius A star, the supermassive black hole at the center of our own galaxy, the one whose photograph the Event Horizon Telescope released in May 2022, the mass is about 4.3 million times the mass of the Sun, and the Schwarzschild radius is about 1.27 times 10 to the 10th meters. That is about 0.085 astronomical units. Mercury's orbit is about 0.39 astronomical units. So the event horizon of Sagittarius A star is much smaller than Mercury's orbit, about 1/5 the size. For M87 star, the supermassive black hole at the center of the galaxy M87, whose photograph the Event Horizon Telescope released in April 2019, the mass is about 6.5 billion times the mass of the Sun, and the Schwarzschild radius is about 128 astronomical units. That is wider than the orbit of Pluto, which sits at about 39 astronomical units. The event horizon of M87 star is wider than our entire solar system out to Pluto, and then more than 3 times wider again. For Thione 6181, of the largest known black holes in the observable universe, at about 66 billion solar masses, the Schwarzschild radius is roughly 1,300 astronomical units, about a 60th of a light year. These are real objects. Their Schwarzschild radii are real distances. The equation we are reading describes the geometry of spacetime in the regions outside these objects. It also, secretly, describes the geometry of space-time in the regions inside these objects. We are about to find out what that second description says. Look at the bracket, 1 minus r sub s over r. Outside the horizon, that is, at distances r greater than r sub s, the fraction r sub s over r is less than 1. So 1 minus r sub s over r is positive. The bracket is positive. Right at the horizon, at r exactly equal to r sub s, the fraction r sub s over r is exactly 1. So 1 minus r sub s over r is 0. The bracket vanishes. Inside the horizon at distances r less than r sub s, the fraction r sub s over r is greater than 1. So 1 minus r sub s over r is negative. The bracket has flipped sign. That is the whole story. That is the whole flip. The bracket flips sign at r equals r sub s, and on either side of that surface, the same algebraic expression describes two physically different geometries. Watch what happens to the time term. Outside the horizon, the bracket is positive, so the time term, with its minus sign out front, is negative. The change in t squared is multiplied by a negative coefficient. In the language of the previous chapter, that is what makes t the time-like coordinate. The negative sign in front of the differential is the signature of time. Inside the horizon, the bracket is negative. The time term still has the minus sign out front. Minus a negative is positive. So inside the horizon, the change in t squared is multiplied by a positive coefficient. The negative sign is gone. The signature of time is gone. The coordinate that, outside the horizon, was the time coordinate has lost the property that made it time. It has become space-like. Now watch the radial term. Outside the horizon, the bracket is positive, so the reciprocal of the bracket is positive. The change in r squared is multiplied by a positive coefficient. Positive coefficient on a differential is the signature of space, so r is space-like. That is the signature of distance. Inside the horizon, the bracket is negative, so the reciprocal of the bracket is also negative. The change in r squared is multiplied by a negative coefficient. Negative coefficient on a differential is the signature of time. So r has become time-like. The coordinate that, outside the horizon, was a measure of how far you are from the center, has become a measure of how far you have left in time. The radial coordinate has become a clock. The time coordinate has become a ruler. They have swapped jobs. This is not metaphor. This is not interpretation. This is what the equation says when you read it. The signs flip. The bracket goes negative. The role of each coordinate, defined entirely by which of them carries the negative sign in the metric, switches. A sign in an equation. The same sign in the same equation. Two different sides of a single invisible surface. Outside, the world you know. Inside, every causally permitted direction leads to smaller r, the way every causally permitted direction in your living room leads to a later time. The singularity at r equals 0 is not a place where space ends. It is a future moment that no world line inside the horizon can avoid. It is, in the deepest possible sense, your own future. If this lands too fast, hold on. We are going to make it land at 3 different speeds, in 3 different visualizations, before this video is over. The math is in front of us. The math is done. From here, we draw it, then we feel it, then we put it into a real photograph of a real black hole, and let the numbers settle into the picture you have already started building. Part 5. Light cones tipping. I want to draw you a picture. We are going to do it in your head, slowly, so that even if you have your eyes closed, it builds anyway. Picture a flat sheet of paper. The paper is a space-time diagram. The vertical direction is time. Up is the future. Down is the past. The horizontal direction is one chosen spatial axis, left and right are just space. two opposite directions you could walk in. Now, at the center of the page, mark a single dot. That dot is you, right now. That dot is an event, a particular place at a particular time. From that dot, two diagonal lines extend upward and outward, one to the upper left, one to the upper right. They go at 45 degrees. Those two lines are the paths of light, leaving the dot in the two directions on this axis. Light going left, light going right. The angle is 45 degrees because we have chosen the units so that 1 second on the time axis equals 1 light second on the space axis. The wedge between those two lines, opening upward into the future, is what physicists call the future light cone. Every place inside the wedge is a place a slower-than-light signal could reach. Every place outside the wedge is too far for any signal to get to in the elapsed time. The wedge is your causal future. Everything you could ever influence with a signal traveling at the speed of light or less is inside that wedge. There is also a wedge opening downward, the past light cone, containing everything that could have influenced you. Everything you could ever know about every photon that has ever reached your eyes, every gravitational wave that has rippled past you, every neutrino that has slipped through you is somewhere inside that downward wedge. This picture, the two wedges meeting at the dot, the future opening up and the past opening down, is the geometry of causality. It is the picture you carry around with you, implicitly, every moment of your life. Forward in time, you have access to a wedge. Backward in time, you have a wedge. Sideways in space, more than the light from a few moments ago could have crossed, you have nothing. Now, I want you to introduce a mass into the picture. Place it off to the right of your dot. Not a black hole yet, just a star, a regular, ordinary star. What happens to the future light cone is subtle, but it matters. The light cone no longer opens straight up. It tips slightly to the right, toward the star. The two diagonal lines that bound the cone are no longer exactly 45 degrees. The right edge tips inward a little, toward the mass. The left edge does too. The whole wedge has a small bias toward the star. The reason is general relativity. Gravity is not, in this theory, a force pulling things toward the star. Gravity is, in this theory, a tilting of the local light cones toward the star, such that moving forward in time already means moving slightly toward the star, unless you actively resist. The tilting of the cones is gravity. There is nothing else. This is why apples fall and planets orbit. The future light cone at every event in the sun's gravitational field is tipped toward the Sunday. To stand still in space, to stay at the same distance from the sun, you have to push against the tipping. The Earth, in its yearly orbit, is doing exactly that, sideways, by moving fast enough laterally that the tipping always lands it on a different point of the same circle. Now, bring the mass closer. Or, equivalently, increase the mass without moving it. The cone tips more. Now bring the mass much closer. Or make it so dense that it has shrunk inside its own Schwarzschild radius, turn it into a black hole. The cone tips a lot. Sit your dot just outside the event horizon. Look at the future light cone. The right edge, the edge pointing toward the black hole, is no longer at 45 degrees. It has tipped substantially toward the black hole. The left edge, the edge pointing away from the black hole, has tipped less. The wedge is asymmetric. Most of the wedge points inward, but the left edge is still pointing upward and to the left. There is still a slice of the cone, a thin slice, that points away from the black hole. That slice is the part of the future you can still escape into. A photon emitted to the left, an astronaut firing their rocket leftward can still get out. The cone has tipped, but not all the way. Now move your dot to exactly the event horizon. The right edge of the cone tips all the way over until it is vertical, parallel to the horizon's surface. A photon emitted to the right, outward, no longer climbs upward on the diagram. It slides sideways, forever. It is moving at the speed of light, but it is not gaining ground against the geometry. It hangs there. Time passes on the diagram, but the photon stays at the same radial position. It is doing the most useless work in physics, running flat out, with zero net progress. The left edge of the cone still tilts inward, a little more than vertical. Most of the cone now points toward the black hole. Only the right edge, the marginal escape edge, is exactly vertical. There is no escape direction left. There is only the marginal hovering direction, which is the limit case. This is what the event horizon is, in light cone language. It is the surface where the outgoing light ray, the ray heading straight away from the center, has been tipped to exactly vertical. No further out, no further in. Just hovering. Now move your dot one tiny step inside the horizon. Both edges of the cone tip past vertical. The right edge, what was the outgoing direction, now tips inward towards smaller r. The left edge, what was the ingoing direction, tips inward even more. The entire cone is now tipped to the left on the diagram, away from the original outward direction, towards smaller r. There is no future pointing direction left that has increasing r. Every direction in the wedge points to smaller r. Every direction inside the cone leads to the singularity. The light cone has not been broken. The light cone has not been rotated. The light cone has been tipped smoothly, continuously, by a geometry that has been getting curvier and curvier all along until it points entirely radially inward. This is the picture. The picture is the same fact we wrote down in the previous chapter with signs and brackets, but now you do not need the signs. You can see it. The cone tips. The future, which used to point upward in time, now points inward in radius. This is what we mean when we say space and time switch roles. We mean the future light cone, which is the geometric carrier of the future, has rotated. Out there, the future was up the time axis. In here, the future is down the radial axis. The thing that points to the future has rotated by 90 degrees. The math knew, the diagram knows. The cone has tipped. Sit with that for a moment. The future, for everyone inside the horizon, points radially inward, not because of a force pulling them in, not because gravity is so strong, it overwhelms their rocket. Because the geometry of cause and effect, the local Lorentzian structure of space-time, has tipped to the point where the only directions in the future are directions of decreasing r. The future, for everyone inside the horizon, has become the singularity. I am going to repeat that because of all the sentences in this video, it is the one I most want you to carry with you afterward. The future, inside a black hole, is the singularity. The singularity is not a place. The singularity is what the future has become. There is a related way of seeing this, which I want to walk you through before we move on, because it sharpens the picture in a useful way. Consider, again, the light cones at different positions outside the horizon. At every event, the cone has the same physical meaning. It bounds the set of events causally accessible from that event. But the cones at different places point in different directions, because gravity tips them, because the geometry around a mass is curved. The cones, as a family, form a kind of vector field across the diagram. Each event has its own cone, and the cones rotate smoothly as you move from event to event. What you have, looking at this family of cones across the diagram, is something like a wind that points in the direction of the future at every place. Far from any mass, the wind points straight up toward later times. Near a mass, the wind tips inward. Near the horizon, the wind tips a lot. Inside the horizon, the wind has rotated past horizontal. The wind blows radially inward. The wind never blows backward. The wind is always future pointing. It is just that future pointing is a local notion defined by the local cone and the local cone rotates as you move across the curved geometry. The role swap is, in this picture, simply the fact that the wind inside the horizon blows radially, not upward, not outward, radially inward. Every leaf carried by that wind ends up at the singularity. There is no place in the interior where the wind blows in any other direction, because there is no event in the interior where the local light cone has any other orientation. If you have ever seen wind streamlines plotted on a weather map, this is the picture. Streamlines, curling toward a center. Every streamline ends at the center. The center is not a high-pressure or low-pressure point in the meteorological sense. The center is, in this geometric sense, a future moment that every streamline reaches in finite proper time. I find this picture clarifying because it removes the temptation to think of the singularity as a destination in space, the way the eye of a hurricane is a destination on a map. The singularity is not a destination. The singularity is the inevitable terminus of every future-pointing streamline. The streamlines do not choose to go there. They have no other direction to go. This is what light cones do. They tip until they point at the singularity. And once they point at the singularity, they cannot, by any local maneuver, be made to point anywhere else. Part 6. The future is now radially inward. There is a temptation, when somebody tells you that the singularity is your future rather than a place, to think the statement is a softening, a way of making the inside of a black hole feel less scary. A literary flourish. It is not a softening. It is, if anything, the opposite. It is the precise reason a black hole is something you cannot, by any maneuver in classical physics, escape from once you have crossed its horizon. And the reason is worth dwelling on, because the standard pop science explanation gets it almost exactly backwards. The standard pop science explanation says, a black hole has such strong gravity that even light cannot escape. The escape velocity at the event horizon equals the speed of light. Anything moving slower than light gets pulled in. The black hole is a kind of cosmic pit with very steep sides, and you slide down to the bottom because the sides are steeper than your engines can climb. This story is not wrong, exactly. The escape velocity at the horizon does equal the speed of light. The mass really is concentrated enough to bend trajectories radically. The picture of a steep pit is a useful first sketch, but it is wrong about why you cannot escape. The reason you cannot escape once you are inside is not that gravity is too strong for your rocket. It is that there is no outward direction left in your future. Every direction your world line can take, consistent with the basic rule that you cannot exceed the speed of light, points towards smaller r. Your engines cannot help you, not because they are too weak, but because the direction they would need to push you is not a direction your future has. To see why this is different from gravity is too strong, consider what happens if you do fire your rocket. Outside the horizon, firing your rocket outward slows your fall. Outside the horizon, gravity is a force, in the loose sense, and a rocket can fight it. You can hover, you can climb, you can leave. Inside the horizon, if you fire your rocket outward, meaning in the direction that, on the outside, would have been radially outward, you do not slow your fall in r. You do not climb. You cannot. The direction radially outward is no longer a future-directed direction. It is a past-directed direction. Firing your rocket in the direction that used to be outward is, inside the horizon, equivalent to trying to push yourself backward in time. The rocket cannot do that. Nothing can do that. Causality forbids it. What firing your rocket can do, inside the horizon, is change which time-like world line you are following. It can move you among the possible future-directed paths. But all those paths still end at r equals 0. All those paths have, at every instant, decreasing r. The most you can do by firing your rocket in any combination of directions is choose how quickly your R decreases. And this is the part that has the gentlest possible weight to it. The maximum proper time you have, the maximum amount of your own life remaining, is achieved by doing nothing. By not firing your rocket at all, free fall is the longest path. The geodesic, the unaccelerated world line, the path your body would naturally follow if you did not push against anything, is the path of maximum remaining proper time. Any acceleration in any direction strictly reduces the time you have left. The formula for the maximum free fall proper time, from the moment of crossing the horizon to the moment of hitting the singularity, is one of the most beautiful in physics. It is pi times g times m divided by c cubed. Equivalently, pi times the Schwarzschild radius, divided by twice the speed of light. Plug in the numbers, and you get specific durations for specific black holes. For a stellar mass black hole, 3 solar masses, the kind you might form from the core of a massive star at the end of its life. The maximum proper time from horizon to singularity is about 46 microseconds, 46 millionths of a second. Less than the time it takes a single oscillation of an ordinary radio wave. For Cygnus X1, a real black hole about 30,000 light-years away, with a mass of about 21 solar masses, the maximum proper time is about 320 microseconds, about a third of a millisecond. For Sagittarius A star, the supermassive black hole at the center of our own galaxy, with a mass of about 4.3 million suns, the maximum proper time is about 66 seconds. A minute and 6 seconds, give or take. For M87 star, the supermassive black hole at the center of M87, with a mass of about 6.5 billion suns, the maximum proper time is about 27.7 hours, a little more than a day. If you cross the event horizon of Ms 87 star and did nothing, you would have about a day on your wristwatch before you reached the singularity. A day to think. A day to feel anything you could feel. For TON 618, one of the largest known black holes, at about 66 billion solar masses, the maximum proper time is about 12 days, almost 2 weeks. 2 weeks inside the horizon, falling freely, before the radial coordinate ran out. These numbers feel weirdly humane. The largest black holes are the gentlest executioners. Their event horizons are so vast wider than the orbit of Pluto, sometimes wider than a light day, that the trip from the horizon to the center, even at the speed light itself would have, is measured in hours or days. You would not be torn apart at the horizon. You would not feel anything at the horizon. You would have a normal feeling existence for some long stretch of time in the interior of a region where the radial coordinate had become your clock. And during that stretch, you would have a strange new fact about your own situation. The longer you wanted to live, the less you should do. This is, in some sense, the opposite of everything an organism on Earth has ever evolved to do. Every instinct you have for self-preservation involves activity, running away from danger, fighting back, moving, doing, struggling. None of those instincts help inside the horizon. Every one of them shortens your remaining life. The black hole is the one situation where survival, defined as maximum proper time, requires the surrender of all motion. The doomed astronaut who keeps their head, sits still in their spacecraft, and does not fire any rockets, that astronaut lives the longest. They are not winning, but they are losing the slowest. This is the gentlest possible executioner, and the strangest possible reframing of the act of dying. Not a struggle, not a fight. The longest path is the one taken by the person who lets go. I am not going to dwell on this. We are talking about physics, and the physics here is geometry. But the physics in this corner of the universe has a shape that is worth letting land for a moment. The future inside a black hole has the property that every effort to outrun it shortens it. Every effort to fight it brings it closer. The future, inside a black hole, has the geometry of an inevitability the listener has perhaps already met, somewhere in their own life. Not exactly, not in detail, but in shape. We are going to keep going. We are going to keep coming back to this fact, because it is the fact, but the next chapter belongs to history, not feeling. We are going to find out how, in the 44 years between Schwarzschild's letter and Kruskal-Szekeres, the physics community failed, again and again, to read the equation that was in front of them. Part 7. 44 years of not seeing it. Schwarzschild's solution was published in 1916. The maximally extended Schwarzschild geometry, the version that makes the role swap unambiguous, and the singularity visibly a moment in time, was not understood until 1960, 44 years. For 44 years, the smartest physicists alive looked at Schwarzschild's equation, an equation that fits on a single line, and either misinterpreted it or refused to take it seriously. The equation did not change. The math did not change. The people changed. The first stage was confusion about the divisions by zero. Schwarzschild's line element, written in his original coordinates, has the bracket 1 minus r sub s over r appearing twice. At r equals r sub s, the bracket is 0. That means the time term has a coefficient of 0 and the radial term has a coefficient of infinity. The equation, taken literally at r equals r sub s, says nothing happens in the time direction and everything is impossibly stretched in the radial direction. The mathematics has a wall at r sub s. Schwarzschild himself noticed this. He treated r sub c, what we now call the Schwarzschild radius, as a curious feature of the solution, the place where his coordinate description broke down, but he did not interpret it as anything physically real. He thought of it as a sort of mathematical scaffolding artifact. In the years after his death, the prevailing view solidified into something stronger. The wall at r sub s was real, the consensus said. It was a singularity in the geometry. It was a place where the laws of physics broke down. Nothing could ever pass through it, because nothing was even defined on the other side. The equation simply did not apply for r less than r sub s. This was, in 1916, a perfectly reasonable position. The mathematics had a divergence. Divergences usually indicate a breakdown. The conservative move was to treat the divergence as a physical limit and assume that real matter, in real situations, would never be compressed below r sub s anyway. Einstein himself argued exactly this. In 1939, in a paper published in the Annals of Mathematics, he argued on physical grounds that no collection of particles could ever be assembled into a configuration tighter than its own Schwarzschild radius. The particles, he argued, would have to be moving at the speed of light to hold themselves together at that density which is forbidden, so the configuration is forbidden. The Schwarzschild radius, Einstein concluded, marked a boundary that real matter would never cross. He was wrong. The argument was a static argument, and it missed the dynamical case. Stars collapse. When a star runs out of fuel and gravity wins, the inward collapse does not stop at any particular radius, unless something else, degeneracy pressure, nuclear pressure, fusion pressure, pushes back. For a sufficiently massive stellar core, nothing pushes back hard enough. The core collapses through its own Schwarzschild radius and keeps going. Robert Oppenheimer and Hartland Snyder showed exactly this in a paper that came out in 1939, the same year as Einstein's no-collapse argument. They wrote down the geometry of a homogeneous spherical dust cloud collapsing under its own gravity and showed that there is no barrier at r sub s. The cloud passes right through. Einstein and Oppenheimer's papers appeared in the same year, in the same field, and pointed in opposite directions. Einstein's was more famous and was widely believed. Oppenheimer's was overshadowed by the start of the war and by Oppenheimer's own move into the Manhattan Project. The physics community continued, on average, to treat R sub s as a wall. Arthur Eddington, the great British astrophysicist, had already, in 1924, written down a coordinate transformation that smoothed out the apparent singularity at R sub s. He did it almost as an aside in a paper titled A Comparison of Whitehead's and Einstein's Formulae, published in Nature. He used what we would now call advanced Eddington-Finkelstein coordinates, a coordinate system in which the surface r equals r sub s is perfectly regular and crossable. He did not realize what he had done. The coordinates were a technical convenience. He used them. He did not interpret the regularity at r sub s as meaning the horizon was crossable. He left that interpretation for later. The interpretation finally came in 1958 in a paper by David Finkelstein in Physical Review, titled Past-Future Asymmetry of the Gravitational Field of a Point Particle. Finkelstein, building on Eddington's coordinates, recognized that the surface, r equals r sub s, is not a singularity. It is a one-way membrane. You can fall through. You cannot climb back. There is a well-defined interior, with its own geometry, and the geometry inside is not the same as the geometry outside. Finkelstein was the one who said it out loud. 34 years after Eddington wrote the coordinates down, 42 years after Schwarzschild's solution. 2 years later, in 1960, two physicists independently produced what is now the definitive resolution, Martin Kruskal at Princeton and George Sekeres in Australia. Kruskal published in Physical Review, volume 119, page 1743. Sekeres published in a Hungarian mathematics journal, Publicationes Mathematicae Debrecen, volume 7, page 285. Neither knew of the other's work. They derived the same thing within months of each other. What they derived is now called the Kruskal-Sekeres coordinate system. In these coordinates, the entire Schwarzschild geometry, both sides of the horizon, the exterior and the interior, the static outside and the dynamic inside, can be drawn on a single diagram with the horizon visible as a 45-degree line through the center, with the singularity visible as a horizontal hyperbolic curve at the top, and with no divisions by zero anywhere. The Kruskal-Sekeres diagram is the picture that finally makes everything land. In the diagram, the four regions of the maximally extended Schwarzschild geometry are all visible at once. Region 1, our exterior universe. Region 2, the black hole interior. Region 3, a parallel exterior universe, geometrically identical to ours but causally disconnected from us. Region 4, a white hole interior, the time reverse of region 2, from which things emerge into the exteriors, but into which nothing can fall. World lines in the diagram are at most 45 degrees from vertical. The horizon is the 45-degree boundary between regions 1 and 2. Below that boundary, you are outside. Above that boundary, you are inside. The singularity is a curve at the top of region 2, and it is drawn horizontally because it is, in fact, a space-like hypersurface. Every world line in region 2 ends on the singularity, not because of a gravitational pull, but because the singularity is in the future of every point in region 2. The Penrose diagram, drawn by Roger Penrose in the late 1960s, takes this one step further. It conformally maps the entire spacetime to a finite region of the page, so that infinity becomes a line at the edge of the diagram. In the Penrose diagram of a Schwarzschild black hole, the singularity is a jagged horizontal line in the future. The two horizons are 45-degree lines. The two exteriors are triangular regions, one to the left and one to the right. The interior region is a triangle above the horizons, with the singularity as its upper edge. The Penrose diagram makes the role swap visually inescapable. The singularity is horizontal. In a space-time diagram, horizontal lines are space-like. The singularity is therefore a moment in time, not a place in space. This took 44 years. In those 44 years, the equation did not change. Schwarzschild's line element, written in his original coordinates in 1916, was the same line element written by Kruskal and Sekeres in their new coordinates in 1960. The geometry was the same. The role swap was the same. What changed was the language. What changed was who was looking. What changed was the willingness of the physics community to take seriously the idea that the surface at R sub s could be crossed, that the interior was real, that the inside of a black hole was a place where R had become time. I find this delay clarifying rather than embarrassing. The physicists were not stupid. They were facing a result that required them to abandon something more fundamental than gravity. They were facing a result that required them to abandon the universality of the labels space and time. They were being told that, in some regions of the universe, the difference between time and space is local. That is a hard thing to absorb. It took the smartest people on the planet 44 years to absorb it, and they were working on it full time. You and I have the advantage of hindsight. The Kruskal-Sekeres diagram is sitting in textbooks now. The Penrose diagram is in every introductory general relativity course. The equation, read carefully, has been read by everyone in the field. The role swap is no longer controversial. It is no longer counterintuitive in the way it was in 1916. It is simply true. But the truth has the same shape it had in Schwarzschild's tent. The bracket flip sign. The coordinates trade jobs. The singularity becomes a future. The chair you are sitting in is held together by a rule that, somewhere in the universe, has rotated. Now let us look at the geometry one more time, in a completely different language. Not algebra, not light cones. A river. Part 8. The River Model. Andrew Hamilton is an astrophysicist at the University of Colorado in Boulder. Jason Lyle is a colleague. In 2008, they published a paper in the American Journal of Physics, Volume 76, page 519, titled The River Model of Black Holes. A preprint of the same paper had circulated on the arXiv since 2004 with the identifier GR-QC/04111060. The paper is one of the most pedagogically beautiful things written about black holes in the past century. It does something the equations cannot quite do on their own. It gives you the role swap as a story about motion. The setup is this. Instead of thinking of space as a fixed stage on which things move, imagine space itself is a river. The river is flowing radially inward, toward the center of a black hole, at a particular speed that depends on how close to the hole you are. The speed of the river, in their model, is exactly the Newtonian escape velocity. At that radius, the speed of light times the square root of r sub s divided by r. Far from the black hole, the river is slow. The speed is much less than the speed of light. You can swim against it without much effort. You can move outward. You can stay still. You can wander. As you drift closer, the river picks up speed. At a particular radius, let us say a few r sub s out, the river is flowing at, say, a third of the speed of light. A photon swimming outward through this river is moving outward at exactly the speed of light relative to the water, but the water is flowing inward at a third of the speed of light, so the photon's net outward motion is 2/3 of the speed of light. Slower than usual? but still outward. The photon makes net outward progress. Closer in, the river is faster. The photon is still moving outward at c relative to the water, but now the water is faster. The photon's net outward speed is smaller. It still climbs, but the climb is exhausting. At one particular radius, the river is flowing at exactly the speed of light. That radius is r sub s, the event horizon. A photon at r equals r sub s, swimming outward, is moving outward at exactly c relative to the local water. The water is moving inward at exactly c. The two velocities cancel. The photon hovers at exactly r equals r sub s, running at full sprint, going nowhere, forever. Inside r sub s, the river is moving faster than light. A photon, locally, can never exceed c relative to the water. It is always swimming at c relative to whatever water it is in. So at any radius less than r sub s, where the water is moving inward at more than c, the photon's outward swim cannot keep up with the inward flow. The photon's net motion is inward. It is being carried backward by a current it cannot outrun toward the center. This is the river model. The interior of a black hole is a region of space-time in which space itself flows inward faster than light. Nothing locally exceeds c. Nothing breaks the rule. But the rule applies relative to the local water, and the local water is moving inward faster than c. The phrase space-time itself falls inward faster than light is not a slogan. It is the literal description of the geometry in these coordinates. Stop and think about how this connects to everything we have built so far. The light cone picture said, the future cone tips, until at the horizon it is parallel to the surface, and inside it tips past the surface. The river model says, the river hits the speed of light at the horizon, and inside it is supraluminal. Same statement, different language. The cone tipping past vertical is the river moving faster than c. The coordinate flip said, inside the horizon, r becomes the time-like coordinate, and the future of every world line has decreasing r. The river model says, inside the horizon, the river is carrying every object towards smaller r, faster than any signal can swim against it. Same statement, different language. The fact that r is time-like is the fact that the river is supraluminal. 3 pictures, 1 geometry. They are all saying the same thing. I find the river picture particularly useful for one specific question, which is the question of escape. People often ask, why can a sufficiently powerful rocket not escape from inside a black hole? The light cone picture answers this by saying, there is no future direction with increasing r. The coordinate flip picture answers this by saying, increasing r is a past-pointing direction which no causal world line can take. The river picture answers it most viscerally. The river is flowing inward at more than c, and you cannot swim upstream against a supraluminal current. The rocket is irrelevant. The engines are irrelevant. The thrust is irrelevant. There is no current, no anything in this universe that flows outward inside the horizon. The river is one way. You are in the river. You go where the river goes. But, and this is the part the river model makes peculiarly humane, you can still move within the river. You can swim sideways. You can swim downstream. You can hold your body still relative to the water. None of these maneuvers brings you outward, but they all have meaning. They all change how quickly you reach the singularity. They all let you, in some sense, choose your trajectory through the inside of the geometry. And the choice that maximizes your remaining proper time, the choice that gives you the longest possible run inside the river, is the same choice the previous chapter pointed out. It is the choice to do nothing, to drift, to let the river carry you without struggling. The black hole is a river. The river is a one-way street. The street is faster than anything that lives, and the gentlest way to ride it is to stop swimming. I keep coming back to this image because of all the metaphors physicists have produced for the inside of a black hole. This one feels closest to what the equations actually say. Not a pit, not a hole, not a moor, not a trap, a river, a direction, a flow. If the listener is drifting now, drifting in their actual living room, in their actual chair, with their eyes closed or half open, or watching the screen with that particular floating attention that comes near sleep, drifting in that way is not, in this geometry, an inappropriate response. The interior of a black hole is, in some real sense, what a perfectly even drift looks like to a creature inside it. A river they cannot leave, a future they cannot prevent, a current that does not require their participation. Tonight, I want you to hear all three of these pictures as one picture. The sign in the equation. The light cone past vertical. The river faster than light. They are three languages for one fact. The fact is that the inside of a black hole is a region of space-time in which the future has rotated. We have, by now, given that fact almost everything we can give it from the inside. We have written it as algebra, drawn it as geometry, and floated it as motion. From here, we are going to do something different. We are going to give it numbers. Specific, real-world numbers, attached to specific, real-world objects. How long, in actual seconds and hours and days, does the interior of a real black hole last? What can the equations tell us about real black holes that have been photographed and heard? Part 9. Max proper time and what freefall actually means. Let us put numbers to the inside of a black hole. The formula for the longest possible proper time from the event horizon to the singularity in a non-rotating uncharged Schwarzschild black hole is pi times g times m divided by c cubed. We can simplify this. Pi times g divided by c cubed is a constant. Multiplied by the mass of the central object, the formula collapses to a single useful rule of thumb. The longest possible interior lifetime, in microseconds, is roughly 15.4 multiplied by the mass of the black hole in solar masses. 15.4 microseconds per solar mass. This number is, in some ways, the strangest thing in the whole video. If a black hole has the mass of one sun, you have, after crossing its event horizon, 15.4 microseconds of life left, no matter what you do. 15.4 millionths of a second. Less than the time it takes a sound wave to travel 1 centimeter through air. If the black hole has 10 solar masses, you have 154 microseconds. Still less than 0.2 of a millisecond. Less than the time it takes a single beat of a hummingbird's wing. If it has 1,000 solar masses, you have about 15.5 thousandths of a second, about 1/60th of the time it takes you to blink. But the relationship is linear in mass. Mass grows, time grows. Every factor of 1,000 in mass is a factor of 1,000 in interior lifetime, and black holes come in a startling range of masses. Sagittarius A star, the supermassive at the center of our own galaxy, is 4.3 million solar masses. Multiply 15.4 microseconds times 4.3 million, that gives us about 66 seconds. A minute and 6 seconds, give or take. If you cross the event horizon of Sagittarius A star, which, depending on your trajectory, would be a brief, undramatic moment, no jolt, no flash, no boundary felt at all, you would have just over 1 minute of life remaining. 66 seconds, in which the radial coordinate of your position was the only clock you had. M87 star is 6.5 billion solar masses. Multiply again, 27.7 hours, slightly more than a day. The interior of M87 star, in freefall proper time, lasts a little more than 24 hours. You could cross its horizon, eat a meal, look around, sleep, wake, and still be falling. Ton 618, an ultramassive quasar in the constellation of Canes Venatici, at about 6.6 times 10 to the 10th solar masses, 66 billion suns, has an interior free-fall time of about 12 days, almost 2 weeks inside the horizon, a fortnight of falling. These numbers are weirdly humane. The biggest black holes are the gentlest executioners. Their interiors last days. Their horizons are spread out over distances larger than the orbit of Pluto. Inside, you would have the strange luxury of time. You would have, in the literal sense, all the time in your world, and there would be no escape from the using of it. This linearity in mass, the bigger the black hole, the longer the interior, is a consequence of the same scaling that makes the Schwarzschild radius proportional to mass. The radius of the event horizon scales with mass. The maximum proper time inside scales with mass. The interior of a black hole is bigger and longer lasting in exactly the same proportion. Doubling the mass doubles the size and doubles the duration. Now, the formula gives the maximum. The longest possible interior lifetime. The longest possible interior lifetime is the lifetime of the free-fall geodesic, the world line of a body that fires no engines, makes no maneuvers, simply drifts inward with the geometry. If you fire engines, you reduce this time. That is the part that takes the longest to absorb on first contact with the geometry. In ordinary life, firing engines is the way you stay alive. The astronauts on the International Space Station are alive in part because of their station-keeping thrusters. The pilots of every plane are alive because they manipulate engines. Vehicles are extensions of our muscles, and muscles, at their core, are the way mammals stay alive in the world. Inside a black hole, engines do not save you. Engines shorten your remaining time. The reason is not mysterious once you have absorbed the sign flip. Free fall is the geodesic. The geodesic is the path of maximum proper time between two events. It is the analog, inside the curved geometry of a black hole, of the straight line between 2 points in flat space. A straight line is the shortest distance. A geodesic is the longest proper time. Any deviation from the geodesic, any acceleration, any thrust, any push gives you a path of shorter, proper time, always. Outside a black hole, geodesics are orbits, the natural motion of a body in a gravitational field with no engines firing is to orbit. The Earth orbits the Sun on a geodesic. You yourself, when you fall down a flight of stairs, are momentarily on a geodesic. Free fall is, everywhere, the natural unaccelerated motion. Engines deviate from this. Inside a black hole, geodesics still exist. They are still the longest proper time paths. They still represent the natural unaccelerated motion. The only thing different is that every interior geodesic terminates at r equals 0 in finite proper time. Every one. The longest possible interior life is finite, and it belongs to the body that does nothing. This is the gentlest possible executioner. The black hole is not malicious, it is not violent. It is not, in any felt sense, even fast. For a sufficiently massive black hole, the interior is enormous, and the time inside is long, and the drift is gentle. The black hole transports you to your doom by the slowest path available, unless you choose, by your own action, to hasten the journey. I have heard a few physicists describe this property as the cruelest of nature's small kindnesses. The black hole is one of the few situations in the universe in which fighting is worse than surrender, and the cosmos is for once, unambiguously, on the side of letting go. You cannot escape, but you can choose to be peaceful. Even more, you cannot escape, and you can choose how long the inside lasts. The choice is between surrender, which gives you the maximum, and resistance, which gives you less. There is something almost philosophical about this, and I do not want to belabor it, because the goal of this video is physics, not philosophy. But the fact has the shape of a kind of meditation. The longest path is the unfought one. The deepest peace is the one that does not push back. Inside a black hole, this is not a metaphor. It is geometry. It is also worth noting that the formula gives a finite answer for any finite mass black hole. The interior is never infinite. The maximum interior lifetime is bounded. Even for the largest black holes known, the bound is on the order of weeks. Even for hypothetical black holes, the mass of a galaxy, the interior would last on the order of years. There is no infinite reservoir of time inside any of these objects. There is, instead, a precisely calculable upper bound on how long the inside can hold you, and the bound scales linearly with the mass of the central body. And, again, the inside ends at the singularity. The singularity is the moment in time, in your future, that all interior world lines reach. The singularity is not a place. It is a calendar entry that cannot be missed. The chair you are sitting in is held together by a rule. The rule is that T is time and R is space. That rule is local. There are places in the universe where it does not hold. We have photographed objects with such places inside them. The next chapter is about those photographs. Before we get there, one more note on the proper time formula, because the linearity in mass deserves a bit more attention. For a stellar mass black hole formed in a supernova, with a mass between, say, 3 and 20 solar masses, the interior is so brief that no organic process inside it would have time to do anything. The cells of an astronaut would not have time to communicate with each other. The light from one side of the astronaut's body to the other would not have time to make the trip more than a few thousand times before the singularity arrived. Inside such an object, the very concept of experiencing the interior is borderline. The experience is shorter than a brainwave. For an intermediate mass black hole, between 100 and 100,000 solar masses, objects that have been searched for and partially detected by LIGO, but which remain rare in our observational census, the interior is on the order of milliseconds to seconds. Still too short for any biological response, but long enough for a few thousand photons to bounce inside a spacecraft, long enough for some electronic device to register that the radio link has gone silent. For a supermassive black hole, in the millions to billions of solar masses, the interior is the duration of a meal, a workday, or a sleep. The astronaut would have, in principle, time to think, time to write, time to talk. The interior of these largest black holes is a usable amount of time, even though the using of it has only one destination. And for the ultramassives TON 618, the very largest known specimens, the interior is on the order of days to weeks, long enough that the astronaut could conduct a small research program inside, long enough that the interior begins to feel almost like a kind of place to live, except that the rule which makes places possible has rotated, and the place is, in fact, the period before an unavoidable future. All of this scales with mass, perfectly linearly, because the same scaling that makes the horizon larger makes the interior duration longer. The interior is not a separate object from the exterior. The interior is the same geometry, scaled. Whatever you choose for the central mass, the geometry stretches in the same proportion in every direction, including the temporal direction that used to be the radial direction. The chair you are sitting in, again, is held together by a rule. The rule is local. The rule scales. The rule, in the right object, rotates. The rotated rule still has a measurable duration before it terminates. We can write the duration down. Part 10. The interior as a future, not a place. There is an ambient zone here, A slow stretch in which I am going to ask you to do something that, in waking analytical mode, you cannot quite do. I am going to ask you to imagine being inside, not in detail, not with numbers, not with the rocket calculus we just walked through. Just to imagine, slowly, with the patience of a guided drift, what it would be like to be a person inside the event horizon of a very large black hole. Pick M87 star. The black hole at the heart of the elliptical galaxy, M87, 53.5 million light-years from Earth, in the constellation of Virgo, 6.5 billion solar masses. Event horizon wider than the orbit of Pluto, 3 times over. Interior lifetime, freefall, about 27.5 hours. Imagine you are an astronaut in a small craft. You have been falling toward M87 star for years, drifting in from outside, watching it grow. The accretion disk around it, the bright ring of infalling matter that the Event Horizon Telescope, photographed in April 2019, has been pulling closer and brighter for months. The temperature of the photons reaching you has been rising. The wavelength has been compressing. The world outside your craft has been slowly deepening in color. Now you are very close. The Schwarzschild radius is about 128 astronomical units below you. You are perhaps 3 or 4 of those radii out. The accretion disk is below and around you, a roaring sheet of plasma at temperatures into the millions of Kelvin. But you cannot feel its heat. Your craft is shielded, and most of the radiation is passing right through you because you are moving fast enough that nothing has time to interact. You cross the horizon. You do not feel it. There is no boundary. There is no surface. No light flashes. No vibration travels through the craft. The horizon is a global mathematical feature of the space-time, defined by where light can and cannot get out. Local physics at the horizon is perfectly ordinary. The Riemann curvature is finite. The Kretschmann scalar is finite. The tidal forces, for a black hole this large, are gentle, softer than the tidal forces a person feels at the surface of the Earth. You could be reading, you could be eating, you could be sleeping. The crossing would happen, and you would not notice. You notice, perhaps, that the radio link to the outside has gone silent, but it might have gone silent 10 minutes earlier, depending on the orientation. There is no instant at which you can say, with certainty, this is the moment I crossed. Now you are inside. Look at your wristwatch. It is ticking, 1 second per second. Every second feels like 1 second. Your wristwatch does not care which side of the horizon you are on. Your wristwatch is a small machine that compares one of its internal periods to your own perception, and your own perception has not changed. But the dials around you, the dials that read your radial position, your spatial coordinates, have started to behave like a clock. The reading you would have called distance to the central singularity is now the reading that tells you how much time you have left. 27.5 hours at most. Less if you fire engines. The reading you would have called time, in the old exterior sense, the t-coordinate of Schwarzschild, has become a direction in space. You could push your craft in the positive t direction. You could push it in the negative direction. You could push it sideways across the t-axis. These would all be motions in something like a spatial dimension. They would change where in the interior you are, but they would not change how much interior life you have left. The amount of life is set by the r coordinate, which is now your clock. Imagine sitting in the craft, hands flat on the console, watching this slowly land, realizing that your own forward, the direction your wristwatch points, the direction your thoughts flow, the direction your heart pumps, has rotated. It used to point along T. It now points along radially inward R. The same forward, same flow, same sense of 1 second per second. Different geometric carrier. The walls of the craft are still walls. The chair is still a chair. The instruments are still instruments. Nothing inside the craft has changed in any way that a person inside could notice. The geometry has changed only at the level of the relationships between coordinates and observers. Internally, all the local physics is the same physics it was outside. This is the part the equations promise and the imagination has trouble with. The interior is not exotic in any local sense. It is exotic in its global causal structure. Locally, nothing is wrong. Locally, every test passes. The same Maxwell equations describe electromagnetism. The same quantum mechanics describes the atoms in your craft. The same standard model describes the particle interactions. You could perform any local experiment, and it would give the same answer it gives in your kitchen. The only difference is the direction of your future. Look up. There is, in this geometry, a sense in which up still means something, even inside the horizon. Light from the accretion disk that crossed the horizon after you did is now arriving from above. It overtakes you. Photons that fell in later than you, moving at the speed of light, catch up. They reach your craft from the direction that used to be outward. Look down. Light from the original collapsing star that formed the black hole, long before you fell in, is still struggling upward and failing. It appears, to you, to come from below from the direction of the singularity. Photons that have been swimming outward against the supraluminal river for thousands of years, never making net progress, arrive at your eyes from below. They look as though they originated at small r, even though they were originally emitted at much larger r. They have been carried inward by the river while trying to swim outward, so your interior sky is layered. Above you, the recent history of the black hole, everything that fell in after you. Below you, the deep history of the black hole, the original star, the early infalling material, the light that has been climbing in vain. The sky has, in this layout, become a calendar. Up is the future of the interior. Down is the past of the interior. The thing you used to call the night sky is now a timeline you can see. The chair you are sitting in, on Earth, in your living room, it is mapped onto this geometry only by analogy. But the analogy is exact. Your sense of forward, your sense of past and future, your sense of cause and effect, these are local properties of the geometry where you happen to be sitting. The properties hold because the geometry is approximately flat, the masses around you are approximately gentle, and the rule that t is time and r is space holds with high precision in your neighborhood. There are places in this same universe where the rule does not hold. We have photographed objects with such places inside them. We have heard their ringdowns. The geometry is not hypothetical. It is the geometry of real things, and it is in the data. You can drift now. You can drift slowly. The geometry will not change. The river will not slow. The interior will not stop. The black hole, in this gentle picture, is one of the most patient objects in physics. It will take you, eventually, by the slowest possible path. You do not need to think about it. The geometry has it handled. Settle slowly. The next chapter, the 11th, is about the data, the photographs, the gravitational wave signals, the observations that confirm the equations we have just walked through. The data is more comforting than dramatic. It is the way of telling you that all of this is real, but real in a way that has been verified by patient instruments operated by patient teams of people. Part 11. What the telescopes and the detectors have confirmed. The Event Horizon Telescope is not a single telescope. It is a network of radio observatories scattered across Earth, working together as a single instrument the size of the planet. 8 radio telescopes on 4 continents, observing the same target at the same time, combining their signals through a technique called very long baseline interferometry. The result is an effective telescope, with a resolution sharper than any optical instrument ever built, sharp enough to resolve features the size of a single grapefruit on the surface of the Moon. In April of 2019, after years of observation and almost 2 years of data analysis, the Event Horizon Telescope collaboration released its first image. The target was the supermassive black hole at the center of the galaxy M87, the same M87 star we just spent the last chapter falling into. The image is, to my eye, one of the most quietly moving things in modern science. It is not dramatic. It is not crisp. It is a fuzzy orange ring, brighter on the bottom than on the top, slightly asymmetric, glowing against a dark background. The diameter of the ring is about 42 microarcseconds. The mass of the central black hole, derived from the size and shape of the ring, is 6.5 plus or minus 0.7 billion solar masses. The papers documenting the discovery were published in the Astrophysical Journal Letters, volume 875, in a series of 6 papers labeled L1 through L6. The ring is not the event horizon. The ring is brighter than the event horizon because the light comes from hot plasma in the accretion disk, swirling at relativistic speeds. The actual event horizon, the surface at r equals r sub s, the surface across which the roll swap happens, is inside the bright ring in the darker region at the center. The dark region is sometimes called the black hole shadow. The shadow has a particular shape predicted by Einstein's equations, and the image matches that prediction within the resolution of the instrument. What this means is that the geometry we have just walked through, the Schwarzschild geometry, or more accurately the Kerr geometry that describes rotating black holes, of which Schwarzschild is the non-rotating limit, has been photographed. The shape of the shadow agrees with the shape predicted by an event horizon. The interior of M87 star is, by direct visual evidence, the interior of a real object obeying the equations we have read. In May of 2022, the same collaboration released a second image. This one was of Sagittarius A star, the supermassive black hole at the center of our own galaxy, about 26,000 light-years from Earth. The image is, again, a ring, this time with a diameter of about 52 microarcseconds. The mass derived from the image is between 4 and 4.3 million solar masses, consistent with the long-standing dynamical mass estimate from the orbits of stars around the galactic center. The papers are in the Astrophysical Journal Letters, volume 930, papers L12 through L17. Sagittarius A star is much smaller than M87 star in absolute terms, but it is much closer, so the angular size on our sky is comparable. The image is harder to produce. Sagittarius A star varies more rapidly than M87 star because its interior timescale is so much shorter, but it exists, and it confirms the same picture. A black hole with the predicted shadow at the predicted size with the predicted mass. The interior of Sagittarius A star, if we use the formula from Chapter 9, is about 66 seconds of freefall proper time long. 66 seconds. A little more than a minute. Inside our own galaxy, the closest such object to Earth. Now, the EHT images do not, by themselves, prove that the roll swap is what is happening inside. The images only confirm that the space-time outside the horizon matches the prediction. The interior is, by construction, not observable from outside. That is the whole point. We cannot photograph the interior. We can photograph what is consistent with the predicted exterior and infer the interior from the same equations that predicted the exterior. That is what we have done. But there is another line of evidence, a different instrument, a different signal, gravitational waves. In September of 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected its first signal. The signal was the merger of two black holes about 30 solar masses each, about 1.5 billion light-years away. The event is called GW150914. The data showed three distinct phases of the merger. The inspiral, in which the two black holes spiraled toward each other while shedding orbital energy into gravitational waves. The merger itself, a violent moment lasting a few milliseconds, and the ring down, in which the newly formed single black hole oscillated like a struck bell before settling into its final shape. The ring down is the part that matters for our story. When a black hole is perturbed, when something falls into it, or when it forms from a merger, it does not settle instantly. It rings. Specific frequencies, set by the geometry of the final black hole, are excited. The ringing decays over a few milliseconds as the perturbations radiate away as gravitational waves. The frequencies and decay times are predicted with extraordinary precision by the same Einstein equations that gave us the Schwarzschild and Kerr geometries. If the predictions match the observations, the geometry is real. The predictions matched. They matched at the level of about 1 part in 1,000. They matched again at every subsequent detection through the O1 and O2 runs from 2015 through 2017, the O3 run from 2019 through 2020, and the O4 run that began in May of 2023 and is still ongoing as of last year. By the GWTC 3 catalogue, the LIGO-Virgo-Kagra collaborations had logged about 90 high-significance binary black hole mergers. By early 2025, the O4 run had added another 60 or so public alerts. And then, on January 14th, 2025, came GW250114. This event was the loudest binary black hole merger ever recorded. Signal-to-noise ratio of 77:80. So clean and so strong that the ring-down signal contained, for the first time at high statistical confidence, the first overtone of the Kerr quasi-normal mode spectrum, a higher frequency mode that decays even faster than the fundamental, and which had previously been at the edge of detectability. The detection of the first overtone is significant because it provides a test of the no-hair theorem, the prediction that a black hole's geometry is completely determined by its mass and spin. If the no-hair theorem is correct, the frequency and decay rate of every overtone, given the mass and spin of the final hole, is uniquely fixed. If the no-hair theorem is wrong, if the geometry depends on something else, some hidden internal structure, some deviation from Kerr, the overtone frequencies should disagree with the prediction. The frequencies agreed. To 4.1 sigma, the GW250114 ringdown matched the Kerr prediction. The most stringent single-event test of the no-hair theorem to date confirmed that the merger remnant was, to the precision of our instruments, a perfectly ordinary Kerr black hole with the same exterior geometry the equations have always predicted, and therefore the same interior, with the same roll swap, the same sign flip, the same singularity at r equals 0 in the future of every interior world line. There are also, in the same data, searches for echoes for signals that would arise if a black hole had a hard surface instead of a horizon, or if the interior leaked information back through the horizon at the millisecond timescale. The echoes have not been found. Multiple search efforts, applied to multiple events through the O3 and O4 runs, have produced no signal above background. The horizon is, as the equations describe it, a one-way membrane. Light goes in. Nothing comes back out at the energies and timescales we can probe. What this means, taken together, is that the geometry we have spent the last several chapters reading is the geometry of real objects. Photographs of M87 star and Sagittarius A star confirm the predicted shadow and mass. Gravitational wave detections of binary black hole mergers confirm the predicted ringdown. echo searches confirm the predicted absence of a hard interior surface. Every probe of horizon-scale physics that has been tried has matched the equations. The interior, with its roll swap, is the interior the equations describe. The equations have been tested everywhere else they can be tested. We have not directly observed the interior, and we will not directly observe it, because the geometry forbids it. But the interior is the interior of an object whose exterior we have photographed and heard ring, and the exterior matches the equations, and the equations contain the roll swap. The roll swap is real. It happens in our own galaxy right now, inside a real object that you have seen a picture of. I will leave the data here. The point is not to overwhelm with numbers. The point is that the strangeness we have been describing for 10 chapters is not a mathematical curiosity. It is a property of objects that exist. The math we have read is the math that describes the photons that hit the Event Horizon Telescope's mirrors, and the gravitational waves that wiggled LIGO's mirrors, and the orbits of stars that loop around Sagittarius A star every few years. The math is grounded, the math is anchored, the math is real. One more chapter, one more move. We are going to put down the data and the math and the diagrams and the river, and we are going to ask, in plain language, what all of this means for the words we started with the words space and time. Part 12. The singularity is the future itself. We started, almost 2 hours ago, with 2 words, space, time, the most settled words in your vocabulary, the most ordinary labels, the words that you use to describe your kitchen, your evening, your life. We have, in the intervening pages, taken those 2 words and slowly disassembled them. Not because they are wrong, they are not wrong, they are local. They are what the geometry around your chair happens to look like on the small scale at which you live. They are excellent labels for excellent purposes, and they will serve you in all but one circumstance for the rest of your life. The one circumstance is the inside of a black hole. There, the labels rotate. Let us say what we know now, plainly. We know that the space-time interval, the universe's measurement of separation, has a minus sign in front of the time term. That minus sign is the difference between time and space. It is the carrier of cause and effect. Without it, there is no past, no future, no flow. Time is, in the most literal sense, a sign in an equation. We know that, in the Schwarzschild geometry that describes the space-time around a single spherical mass, that minus sign is wrapped inside a factor of 1 minus r sub s over r. Outside the Schwarzschild radius, the factor is positive, and the time coordinate t carries the minus sign in the natural way. Inside the Schwarzschild radius, the factor is negative, and the minus sign moves. It moves from t to r. The radial coordinate r becomes the carrier of cause and effect, and the time coordinate t becomes just another direction in space. We know that this is what the light cones do in geometric language. They tip. Outside, they open mostly upward in time, with a slight inward bias from gravity. At the horizon, the outgoing edge tips to exactly vertical. Inside, both edges have tipped past vertical, and the future cone points radially inward. The future itself, inside a black hole, points towards smaller r. We know that this is what the river of space does, in fluid language. It flows inward. At the horizon, it is moving inward at exactly the speed of light. Inside, it is supraluminal, faster than anything that can swim against it. We know that the consequence is that the singularity at r equals 0 is not a place, it is a moment in time. Every future-directed world line in the interior has decreasing r, the same way every future-directed world line anywhere has increasing t. The singularity is the future of every interior observer, in exactly the sense that next Tuesday is the future of every observer right now. We know that the maximum proper time from horizon to singularity is pi gm over c cubed. For a stellar mass black hole, that is microseconds. For Sagittarius A star, a minute. For M87 star, a day. For TON 618, almost 2 weeks. The interior of a black hole is a finite, calculable amount of time. The biggest black holes are the gentlest executioners. We know that the longest path inside is the unaccelerated path. Free fall is the geodesic is the longest proper time, and any acceleration shortens it. Inside a black hole, the way to live longest is to do nothing. We know that this was hidden inside Schwarzschild's equation from January 1916, and that the physics community did not understand it until Kruskal and Sekkeres independently figured it out in 1960, 44 years. The equation did not change. The people did. We know that the geometry has been photographed and heard. M87 star in April 19. Sagittarius A star in May 22. GW 2501-14 in January 25. The predictions of the equations match the observations at every probe of horizon-scale physics ever made. The roll swap is the roll swap of real objects. And we know, finally, that the chair you are sitting in the room, the evening, the wristwatch on your wrist, is held together by the assumption that T is time and R is space. That assumption holds because of where you are. The geometry around you is approximately flat. The minus sign sits securely in front of T. The rule that distinguishes time from space is, in your neighborhood, robust. But the rule is local. Somewhere right now, in our own galaxy, in our own universe, at a distance of about 26,000 light-years, a real object is sitting with an interior in which the rule has rotated. Across a surface as smooth and featureless as glass, the difference between time and space has flipped. There are observers hypothetical, but observers in the language of the equations for whom the radial coordinate is the clock and the time coordinate is the ruler. There are world lines that exist in our same universe, whose entire future points in a direction we would call inward. This is not separate from the universe you live in. It is part of it. The same equations describe both. The same physical laws apply. The same speed of light is the limit. The same minus sign carries the same flow of cause and effect. The minus sign has just moved. The singularity you should now feel in your body is not a place. The singularity is the future. Not metaphorically, not loosely. In the precise geometric sense in which any future is a future, the locus of events that all causally permitted world lines must reach. The singularity is the future the interior of a black hole has rotated into. I want to leave you with one image. Imagine the listener you, in your living room sitting in a chair. Imagine, just at the edge of perception, a faint outline of the rule that keeps your chair a place rather than a moment. The rule is a sign. The sign sits in front of T. The sign tells the universe that your T coordinate is time and your radial coordinate is space. Now imagine the sign moves, just for a moment, just for an instant. The sign slides from T to R. Your T coordinate becomes a direction. Your radial coordinate becomes a clock. Your chair becomes a moment. Your room, a future. The image does not happen. You are far from any black hole. The rule, in your neighborhood, is rock solid. You will not, in any waking minute of any life you will live, see this happen. But it can happen. It does happen. There are places in the universe where it is happening right now. The places have names M87 star, Sagittarius A star, Cygnus X1, the dozens of black hole binaries seen by LIGO, the supermassive cores of every large galaxy. Inside each of those objects, the sign has moved. The chair is a moment. The room is a future. The vocabulary that lets you describe your evening has rotated. A sign in an equation. A sign in an equation that determines what we mean by time, that determines what we mean by space, that determines what we mean by future. A sign in an equation that, in most of the universe, sits where you expect it to sit. A sign in an equation that, in a few specific objects, has moved. We are, you and I, sitting on the side of the sign where the chair is a place. That is a lucky thing to be doing. It is the side on which an evening can unfold, on which a video can be watched, on which a thought can be followed from one moment to the next. The other side exists. The other side is in the math, in the photographs, in the data. The other side is, in some quiet way, part of the universe you live in. I do not have a tidy ending for tonight. The geometry does not have a tidy ending. The Singularity of a black hole is real, and the roll swap is real, and the singularity is the future, and the chair is still a chair, and you are still here. That is all we have tonight. A sign in an equation. A factor that flips. A coordinate that becomes a clock. A future that points inward. A universe with the strange courtesy of letting most of us live, almost all the time, on the side of the sign where the words space and time still mean what they have always meant. Sleep well if you are sleeping. Drift slowly if you are drifting. The geometry will hold, the chair will hold. The minus sign in your neighborhood will sit where it has always sat. You can rest with that until next time.